Dear students, today I am beginning a new chapter, gamma functions. What is new about this chapter and why do we study here gamma functions? This is the first question. Actually, what you have done in your BSc Part 1 course, you have studied this gamma function, but you have just seen an integral definition of gamma function, and that gamma function was a function of a real variable. This time in theory of generalized functions, when we study gamma function, the domain of gamma function is extended to the complex plane with certain conditions. So first, let us have a look what is gamma function. So what you have studied earlier is definition of gamma function. As I already told you that this definition is for real numbers, and moreover this definition is valid for positive real numbers only, and the definition is in the integral form. It is 0 integral 0 to infinity gamma x is integral 0 to infinity e to the power minus t t to the power x minus 1 dt, where x must be a positive real number. Why this condition there? Why? The answer is that it is an improper integral, and not only because its limit is from 0 to infinity, but also when x is less than 1, there is problem in the neighborhood of 0. As t tends to 0 from the right hand side, this function has problem when x is less than 1. So it's an improper integral especially when x is less than 1. We have to pay attention to it. It can be very easily proved by using standard comparison theorems for convergence of improper integrals, that this improper integral is convergent when x is greater than 0. So this condition is there. Now we extend this definition of gamma function to complex numbers also. If suppose z is a complex number, then in the same way we define the gamma function of z as integral 0 to infinity, again e to the power minus t, but this time t to the power z minus 1 dt, where the condition now becomes real part of z greater than 0. Why this condition? Now this is an important question, that why this condition? Is it analogous to that condition x greater than 0 in some way? So the answer is yes. Why this condition? The answer is because when we deal with the complex numbers or function of complex variables, the modulus, especially in case of convergence, we take the modulus, and when we take modulus of t to the power z minus 1, we can suppose z is since z is a complex number, suppose z is x plus iy, where both x and y both are real numbers. So t to the power z minus 1 and modulus of this can be written as t to the power x plus iy minus 1. So you can directly write x minus 1 plus iota y. So t to the power x minus 1 in another bracket t to the power iy. And you know that a to the power z is e to the power z log or ln a. Now, so we can write t to the iota y as e to the iota y log t. Okay. So now if we assume, or if we suppose that y of t, this term is theta, this term is theta, then we are certainly getting e to the power I theta, and modulus of this, since e to the power I theta is cos theta sine theta by Euler's theorem, so e to the power I theta has modulus 1. So we can directly, what we can write here, simply it will be, it is not n minus 1, actually it is t to the power x minus 1. Yes, t to the power x minus 1. So we can directly write it as mod of t to the power x minus 1. Or if you just pay an attention to what is x, so x is nothing but real part of z. So you can directly write it as t to the power of real part of z minus 1. So in case of gamma function of real variable, the role which was being played by t to the power x minus 1, the same role is now being played by t to the power real part of z minus 1. So since the condition was x greater than 0 in case when x was real, so here the condition is same. You can write the condition in the same way as real part of z should be greater than 0. So this is the answer to that question, why real part of z should be. Now let us see another important expression for the gamma function, and this is also an integral representation of gamma function, and this is gamma z 0 to 1 integral log 1 over y to the power z minus 1 dz. The same condition, real part of z should be greater than 0. The previous definition that I earlier told you, and that you have already studied in your BSc Part 1 course, this definition is of gamma function, and this definition is referred to as Eulerian definition of gamma function. Now, in this course, we will see another definition of gamma function, and that definition of gamma function is due to Weierstrass, and the definition is Weierstrass definition. Weierstrass definition of gamma function, and that definition is 1 over gamma z equals z e to the small gamma z multiplication. This is an infinite product, n is equal to 1 to infinity, infinite product, 1 plus z over n e to the minus z over n. This is an infinite product, and obviously whenever we come across or go across an infinite product or an infinite series, there are certain questions like uniform convergence or absolute convergence of the series or the product. But anyway, this is the Weierstrass definition of gamma function. Now, in this definition, we see a term which we are not familiar with, and that term is this small gamma. What is this term here? This term, small gamma, is a very important constant, and this constant is called Euler constant. What is the definition or what is the value of this Euler constant? Actually, gamma is defined as the limit 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on, 1 over n negative minus log n. So actually gamma is nothing but the limit of this sequence. But in order to prove that this gamma really exists, and in order to and also in order to find in what interval this Euler constant will belong, we need to prove the convergence of the sequence. Whenever we are trying to define some constant as limit of a sequence, we need to prove that this particular sequence is convergent. Now, if the sequence is convergent, obviously it will be bounded, and if it is bounded, then we need to find its bounds also, and those bounds may also be the bounds of this either constant. Now, what we do here, we suppose that 1 plus 1 over 2 plus and so on, 1 over n is un. Okay. So, and overall, this term, suppose this term is an. So, what will be an? An will be un minus log, right? We will show that an is convergent. Sequence an is convergent. Now, if we try to find an plus 1 minus an, what do we get? Actually, an plus 1 will be the summation from 1 to 1 over n plus 1 and minus log n plus 1 also. And if we subtract n from n plus 1, all these terms from 1 to 1 over n will be subtracted. And what we will get only this term 1 over n plus 1. And yes, obviously, since we are subtracting un here, so an here, so we will get plus log n negative of log n plus 1. So it gives us 1 over n plus 1 and plus log n over n plus 1, right? Now, what we can do, we can write it an plus 1 minus an. We can write it as 1 over n plus 1 plus log of 1 minus 1 over n plus 1, since this is n over n plus 1. And now, expanding this log 1 minus x, all the terms will be negative, and the first term will be minus 1 upon n plus 1, and that will cancel out this plus 1 over n plus 1. And so we can say that all the terms will be negative, resulting terms will be negative. So we can directly say that an plus 1 is going to be less than an, and it means that the sequence an is obviously going to be monotonic decreasing. Okay, now we know that if a sequence is monotonic decreasing, you can say monotonic in nature, and it is bounded also, then there is a result saying that the sequence will be convergent. And in particular, if the sequence is monotonic decreasing, and along with that sequence, suppose the sequence is monotonic decreasing, it is trying to have a dip, but if it is bounded below, also, then it will certainly not be able to cross this boundary. So it will certainly converge. To this particular boundary, right? So in that case, the infimum of the sequence, if it is bounded below also, the infimum of the sequence will be the limit of the sequence. So now we need to prove that the sequence an is monotonic decreasing, and along with it, we just need to prove that the sequence an is bounded below. So what we'll do for this, we know from the mean value theorem of integral calculus that small m to b minus a is less than or equal to integral a to b fx dx less than equal to capital M to b minus a, where this small m is infimum of fx in the interval x belongs to the interval ab, and similarly capital M is nothing but supremum of fx in the same interval. Now if we apply this mean value theorem to the function, suppose the function we take is fx equals 1 over x, And let us apply this mean value theorem in the interval small m minus 1 comma small, the interval of length 1. So first we need to make sure that the function must be Riemann integrable. So obviously this function fx is 1 upon x, is since it is continuous in this interval m minus 1 to m, so obviously it is going to be integrable. So we can directly use this mean value theorem for fx equals 1 upon x in this interval also. What will be the infimum? What will be small m here for this 1 upon x? So since this is decreasing, so at m we will this endpoint m we will attain. So infimum of fx will be, I should not use this simple m here because m here I have used for something else. So I directly I write infimum of fx and it will be 1 over m. And what will be supremum of fx? The supremum of fx will be 1 over m minus 1. And we directly substitute the values of infimum and supremum and this function along with the range of integration here. From mean value theorem, we get 1 over small m into b minus a. b minus a is the length of the interval of integration, and that length is 1, is less than equal to an integral m minus 1 to m 1 over x dx, and it is going to be less than equal to 1 over m minus 1 into 1. So directly it gives you log of x, and the range of integration is from m minus 1 to m. So we directly get log of m minus log of m minus 1, and this lies between 1 over m to 1 over m minus 1. Now if we put m as 2, 3, 4 and so on up to n, and add all these results that we obtain from this inequality after putting m equals 2, 3, 4 and so on n, successively adding, we get the left hand side we will get 1 over 2 plus 1 over 3 plus and so on 1 over n, and it will be less than equal to, since this term is difference of two terms, consecutive terms, so after adding the terms will get cancelled and we will ultimately get log of n only, and will be less than equal to, this will start when we put m equals 2 in here. The first term is 1, that 1 over 2, and the last term is 1 less than this last term here, so we will just get 1 over n minus 1 as the last term. Now from here what we can do is, if we add 1 here and subtract 1 from the left hand side, it becomes I think we had assumed this as un. Yes, it was un. So what we can write it as un minus 1 less than equal to log of n, and it is less than equal to, what is this? This is nothing but, if we add 1 over n and then subtract 1 over n, so I should write 1 over n minus 1 over n. This is un from here to here, this is un, and sorry, this is un and minus 1 over n. So we get un minus 1 over n. Now from this, if we take minus sign, minus of log n, then we will get 1 minus un, and it will be greater than equal to minus of log n, because we are taking negative sign, we have multiplied with a minus sign, and 1 over n minus un. Now if we add un to all the sides, to all the terms, we get, in the center we get un minus log n, and un minus log n is nothing but an, and this an will be greater than equal to 1 over n and less than equal to, on the right hand side we will get, then un will get cancelled and we are getting just 1 for every n belongs to n. So from this monotonicity property, or you can say sandwich rule type of thing, not sandwich rule we can apply here, just using monotonicity property, we can directly say that, or you can directly say that 1 over n will always be greater than 0. So an is always going to lie between 0 and 1. It implies that sequence an is bounded, and we have already seen that it is motorically decreasing. It means that the sequence an is nothing but an is a convergent sequence, right? And now since an, all the terms of an lie between 0 to 1, it means that the limit of an will also lie between 0 to 1. So, and this limit is, obviously this is gamma, Euler constant. So it means that the Euler constant gamma lies between 0 to 1, right? So this proves that the sequence here is convergent if limit gamma will be a certain finite real number, and also that real number lies between 0 and 1. Here it is a known fact that the value of this Euler constant gamma is approximately 0.5777215 and so on. Now let us go back to the definition of the Weierstrass definition of the gamma function. Here we see this infinite product, just like the convergence or the absolute convergence of the infinite series is has to be made sure. In the same way, we have to make sure the convergence, or here we will try to prove the absolute convergence of this infinite product. We know that this infinite product will be absolutely convergent if the corresponding series, and what will be that corresponding series? If we take log here, we can write that the corresponding series will be sigma log of 1 plus z over n minus z over n. Now this general term, let us just focus at this general term. If we expand log 1 plus z over n here, we get z over n minus, and the next term will be 1 upon n square into something, then the next term will be 1 upon n cube into something, and the first term z upon n will get cancelled by this minus z upon n. So we will be getting the terms from 1 over n square and remaining the higher powers, and if we take 1 over n square common, we get a series there. And this is since this is the general term, this is of order n to the minus 2, and we know that from the p series that sigma 1 over n to the power p, this series, since this is p is greater than 1, p is 2 here, so this is, we know that this is convergent. So we can directly say that the infinite product that we just saw in the Weierstrass definition is absolutely convergent for all the finite values of z. So we can say that the Weierstrass definition, the infinite product is convergent or absolutely convergent for all z in finite Argand plane. Now there are some other facts also, some very important facts and about the gamma function. First is that gamma z is analytic except z equals 0, minus 1, minus 2, minus 3 and so on, and z equals infinity. Second, gamma z has simple poles at these points. Third point is that gamma z has an essential singularity at this z is equal to infinity. Now, these facts that gamma z is analytic except z is equal to these values, from where these facts come? So what we need to do is we just need to look at this definition. We can see from here that if we just take reciprocal both sides, then gamma z is certainly 1 over z and also 1 over 1 plus z upon n. So because these terms are now in the denominator, 1 over z and 1 over 1 plus z upon n, and at z is equal to 0 and at z is equal to minus n, it means that at z is equal to 0, minus 1, minus 2, minus 3, minus 4, obviously according to this Weierstrass definition, the gamma function ceases to be analytic. And another thing, that it has essential singularity. This is just because we know that limit point of these poles is always going to be an essential singularity. So we can directly write that statement. Now, as an assignment, I give you certain questions. For example, I give you this question to try. Gamma dash z over gamma z is minus 1 upon z. Sorry, it is minus gamma minus 1 over z. I should erase this. Yes. Minus 1 upon z minus gamma plus sigma n is equal to 1 to infinity z upon n into z plus n. So I give you this question to practice, and also some more important questions are there, like one question is gamma dash 1 is minus of gamma, it is negative of Euler's constant, and also gamma dash 1 over 2 divided by gamma 1 over 2 or gamma half, and it is equal to negative of gamma minus log 2. Another important result that you should try is Euler product formula for gamma z. This is also a very important result, and it is gamma z is equal to 1 over z multiplication from n equals 1 to infinity. It is also an infinite product, and bracket we have 1 plus 1 upon n to the power z, 1 plus z upon n to the power minus 1. So this is another very important result that you should try, and this is the well-known Euler product formula for gamma z.